Welcome to the Metabolic Classroom. I'm Benjamin BIKMAN, biomedical scientist and professor of cell biology. In today's lecture, we are uncovering the profound metabolic effects of the hormone cortisol. This is a hormone that, despite its villainization, is necessary for our survival, but it is such a consequential hormone that it might not surprise you to learn that it has some pretty relevant effects when it comes to metabolism, particularly when it is chronically elevated. There are myriad ways to classify hormones. Cortisol is a steroid hormone. That means it's synthesized from cholesterol. It's made in the adrenal cortex. That is the outer layer of the adrenal glands, which themselves reside right on top of the kidneys. It falls into the family of a glucocorticoid. Indeed, it's the main one. As a glucocorticoid, it plays a central role in energy mobilization, immune regulation, and even circadian rhythms. Its production is governed by the hypothalamic, pituitary, and then adrenal axis. Anyone who's had any touching of endocrinology would sound familiar to you. Just to say that again, there is this upper region within the brain, the hypothalamus, which then connects to the pituitary gland. The hypothalamus will send a signal to the pituitary, which will then send a signal via a hormone called ACTH down to the adrenal glands. And then it's ACTH that goes from the pituitary down to the outer peel. It's like the adrenal gland is like an orange, and it has a peel, and then it has the fleshy little part of it. That peel is the adrenal cortex. That's where cortisol is being produced, again, in response to ACTH. If we were to assign any primary function to cortisol, it would be to ensure energy availability, particularly glucose. So cortisol is a very powerful signal in promoting glycogenolysis in the liver, which is the breaking down of glycogen into glucose. It also stimulates protein catabolism in muscle, so thereby breaking down amino acids from the muscle, but to fuel gluconeogenesis. And gluconeogenesis is the term for the liver creating new glucose from scratch. But cortisol also enhances lipolysis, or the breakdown of fat tissue in some depots. That's a very important distinction that we'll get to in a moment. So cortisol will promote the breakdown of fat in certain locations, so thereby moving the stored fat into the blood as free fatty acids to be used for either energy or redeposition, so storing it somewhere else. These actions are crucial during acute stress, times of fasting or danger where you need to get away from something, but chronic elevation due to prolonged stress or medications or disease lead to metabolic function. Cortisol also has a potent anti-inflammatory effect. This is why synthetic glucocorticoids like prednisone, for example, are used therapeutically to help control conditions of chronic inflammation or immune activation, like, for example, autoimmune diseases. At the cellular level, cortisol binds to what's called the glucocorticoid receptors. Now, the glucocorticoid receptors are not on the surface of the cell. In the past, when I've talked about hormone like insulin coming and binding to an insulin receptor, it's something that is on the surface of the cell. The glucocorticoid receptors are deeper within the cell. They're located more, centrally within the cytosol. But when cortisol comes and slips through the cell membrane and binds to the glucocorticoid receptor within the body of the cell itself, it then will translocate into the nucleus. So the glucocorticoid receptor, once bound with cortisol, will move into the nucleus and then will act as a transcription factor. So it will turn on the production or the activation of genes, of numerous genes, which of course, once you turn on the gene, you get eventually what will turn into a protein product, or something will be produced. But some of the genes that are so important in the context of energy metabolism are ones like PEPCK, PEPCK, that stands for phosphoenolpyruvate carboxykinase. That's essential for gluconeogenesis. So that's an essential enzyme that the liver has to activate in order to start making glucose. But the glucocorticoid receptor will also increase the expression of lipoprotein lipase, or LPL, which helps for lipid uptake or fat uptake into various tissues. This gene regulation underlies cortisol's very important and broad metabolic effects. But of course, if it's sustained for too long, you start to get into the realm of pathology. Problems start to happen. And again, we're going to get to some of those. Now, cortisol is one of the more potently circadian hormones. So there's quite a diurnal rhythm to it where it can really peak in the morning, which is thought to just be reflective of the body needing to get some energy before it gets up and starts to get busy. And then it will generally start to decline in the afternoon to evening. If you disrupt that rhythm, like with, say, chronic stress or something, it does set the stage for some other problems. Now, at the most extreme end, we have a condition called Cushing's disease, or Cushing's syndrome. Cushing's syndrome is a vivid illustration of cortisol excess. It's typically caused by a pituitary tumor, or what's called an adenoma, where the pituitary gland has this growth, a tumor, and it is actively dumping out ACTH. So this overproduction of ACTH will go down to the adrenal cortex and result in the overproduction of cortisol. In this situation, the most dramatic effect are the physical changes, and they are striking. The patients will, within just weeks, start to develop a very round, puffy face, or what's called a moon face. They will also have a fatty deposit on the upper back, what's sometimes referred to as a buffalo hump. But in addition to this centralization of fat, where the person's getting a lot fatter essentially from the pubis, or right at the center of the groin area, all the way up to the top, they start to become very, very round right on the body. At the same time, they start to have very thin and fragile skin, where the skin is easily bruised, and they start to get these big purple stretch marks. This can happen anywhere, but especially it's happening on the abdomen, where the person is gaining so much weight. And indeed, weight gain is rapid. It is predominantly central, like I said, with the fat accumulation really occurring on the trunk of the body, while the limbs, like the legs and arms, start to get quite thin. This is a very stark central adiposity. And these very visible changes reflect the profound metabolic shifts. The rapid weight gain and the visceral fat accumulation and the central fat accumulation stem from cortisol's effect on adipose tissue, while the high incidence of type 2 diabetes in these people with Cushing's syndrome points to some disruptions in glucose metabolism and insulin signaling. The metabolic effects are not merely cosmetic. They really do signal a cascade of biochemical changes that we're going to get into now. So let's start by diving into the type 2 diabetes aspect. What is it that cortisol is doing to glucose and insulin in order to put them into such a metabolic harm? And there, it is extensive, but I want to touch on the biochemistry as I go through these descriptions. Cortisol is, as I've said, a potent driver. Indeed, there's almost nothing equivalent of gluconeogenesis, the liver's production of glucose from non-glucose precursors. This includes things like lactate, amino acids, and glycerol. That's the trifecta, the holy trinity of glucogenic substrate. In liver cells, in hepatocytes, cortisol binds the glucocorticoid receptor, which, as I noted earlier, upregulates PEPCK expression and another important enzyme called glucose 6 phosphatase. Now, PepCK is busily converting oxaloacetate. If you think of glycolysis, the breakdown of glucose, always in biochemistry, we look at it as a kind of downward process. So, it'll make sense why I'm sort of pointing in various directions if you keep that paradigm in mind. So, glycolysis is when you have the glucose come into a cell and then you're steadily breaking it down through this catabolic process in order to get ATP. Gluconeogenesis is the inverse. Now we are taking simpler molecules and building them up into glucose. So it's anabolic. Now, at the bottom of this, or at the front end, if you will, the beginning of gluconeogenesis, PepCK is helping to convert a molecule called oxaloacetate into a molecule called phosphoenol pyruvate. And that is some of the first step. But then at the end of it all, right before the liver cell is ready to actually kick the glucose out, that's where you have the glucose 6 phosphatase, because it will take the glucose 6 phosphate and kick off the phosphate, which now allows the liver cell to release a free glucose. That is an enzyme that you don't see elsewhere. Why does the muscle not share its glucose? Well, one reason is it doesn't have that glucose 6 phosphatase. It can't liberate the glucose back into its native form. So the collective effect of all of this, of course, taking the glycogen molecule and snipping it into pieces, getting glucose, or the whole gluconeogenesis, taking any carbons, linking them together into glucose. All of this is this collective effect that ensures that there's going to be energy availability in the form of glucose, in this case, during some scenario, any stressful situation, including even something as seemingly benign as a fast or some prolonged exercise. Now, why is it that that becomes problematic? Of course, well, it's happening all the time when cortisol is elevated, but when you combine it with the insulin resistance, you start to understand how cortisol can promote type 2 diabetes so well. So we have the hyperglycemia that the cortisol is trying to elicit. That alone is going to be increasing the secretion of insulin. But at the same time, cortisol is inducing very strong insulin resistance. Work from some friends and colleagues, Will Holland and Dr. Scott Summers, has elucidated some of the critical mechanism here when it comes to cortisol-induced insulin resistance. And it might not surprise you, anyone who's connected with me in the past knows of my interest and expertise and even affection for a molecule called ceramide. Well, ceramides are one of the most common and relevant intracellular causes of insulin resistance. Cortisol, when it comes to the glucocorticoid receptor, it will stimulate the synthesis or the activation of these enzymes that are involved in the production of ceramides. Now, ceramides are one of the main lipids within a family of fats called the sphingolipids. Sphingo being reflective or from the word sphinx, because the sphinx was such an enigma, such a mystery, and sphingolipids were so poorly understood, and their purpose was so vague for so long that they earned that name. Now, when ceramides accumulate in the cell, like in response to cortisol, it will activate an enzyme called PP2A, protein phosphatase 2A. Then protein phosphatase 2A inhibits the activation of another enzyme called AKT. And without AKT, the insulin signal starts to fall apart. Like, for example, when you look at the muscle cell or the fat cell, how is insulin capable of pulling in the glucose into those cells? Well, in part, it's because it stimulates this AKT, which in turn stimulates GLUT4, allowing glucose uptake, in addition to other downstream signaling effects of the insulin. But if you block that, which cortisol is doing via ceramides, now insulin comes and knocks on the wall of on the muscle cell, for example, and says, hey, I have some glucose here. Can you take it in? The muscle cell's not listening. There's one final point worth mentioning here is that cortisol will also promote muscle protein catabolism, thereby releasing the amino acids from the muscle. So eroding the muscle's substance to dump those amino acids into the blood, so that those amino acids will go to the liver and act as carbon sources for gluconeogenesis. Now, since skeletal muscle is the major glucose sink, and I use that kind of as a term of physics, like a heat sink, something that absorbs a lot of glucose in this case, all of this exacerbates the hyperglycemia. So you think about this. You have the cortisol, which is stimulating the liver to just be dumping glucose into the bloodstream. You have the cortisol causing insulin resistance throughout the body, compromising tissue's ability to pull in the glucose in some instances. And then third, directly eroding the very bulk or substance of the tissue that takes in the most glucose, namely muscle. So collectively, these effects, the hyperglycemia, the insulin resistance, the muscle loss, really create a metabolic storm that explains the rapid rise in diabetes risk. Okay, now when a lot of people think about cortisol, they might not be thinking about glucose, even though they should. That is arguably cortisol's main effect. They often will think about fat tissue. So let's just talk a little bit about fat tissue. As you know, I have a great affection for fat. I am both a great defender of body fat. We need it, of course, but I also appreciate its role in chronic disease more than most. Now, one of the most striking features of cortisol excess is the central adiposity, the accumulation of fat in the abdomen and trunk. To understand this, we need to examine cortisol's effects on adipocytes and compare them. I think it's fun to compare that to insulin's role. And to do so in a minute, I'm going to introduce type 1 diabetes just because it's such an easy example of looking at the effects of insulin. Now, before we get there, fat cells will express glucocorticoid receptors, which upon cortisol binding elevates or regulates genes involved in fat metabolism. Now, what's interesting is that in visceral adipose tissue, so that is the fat surrounding the central organs within the abdominal space, cortisol's effects are amplified. So cortisol is it's activating these enzymes that will actively convert. Actually, it takes a less active version of cortisol called cortisone and then activates it into cortisol. Now, the degree to which this occurs in humans as opposed to rodents is kind of vague. So I want to make that disclosure right up front. But at those central fat cells, cortisol upregulates LPL, lipoprotein lipase. And the lipoprotein lipase is so important because that's what hydrolyzes or pulls off individual fats as triglycerides are circulating through as carried on lipoproteins. Because if a triglyceride, which is the stored form of fat, in fact, stored in fat cells and as moved predominantly through blood, the big triglyceride itself isn't what moves in. And I'm acting like the three parts of the triglyceride. The triglyceride isn't what is moving from the blood into the fat cells. It has to get hydrolyzed, or you have to pull off the individual fatty acids, and that's what moves in. So there are these enzymes, which is LPL, lipoprotein lipase. Well, cortisol will activate it at fat cells in the visceral space. And so it's promoting that uptake. At the same time, it inhibits the hormone-sensitive lipase, which is the enzyme that would be breaking down the fat from those fat cells. So it's activating the enzymes to pull in the fat at the visceral fat cells, but inhibiting the enzymes that would be breaking down that fat. So you can start to see how it's overall promoting greater, it's stimulating the central fat cells. Now, beyond that, if you look at the subcutaneous fat cells, you actually have the opposite. Cortisol is promoting lipolysis in the subcutaneous fat by upregulating hormone-sensitive lipase and adipose triglyceride lipase, ATGL. You could look up both of those for more details if you need to, but those are the enzymes that need to sequentially be activated to take the triglyceride from the fat cell and start pulling off its individual components. Once again, the triglycerides aren't going to freely move between the cell or across the cell membrane. You have to break it down into its component parts. And so to say all of this again, we have two fat depots. We have the visceral adipose and we have the subcutaneous adipose, the fat that is stored beneath the skin, the fat that we can pinch and jiggle. Now, that's the healthier fat. It's a healthier place to store fat. But what cortisol does is that it is selectively promoting lipolysis at the subcutaneous fat, which is why you start to see the limbs start to shrink down as you're losing all that fat. You're burning all the fat at the limbs, but burning is not the right word. You're mobilizing that fat. You're essentially transporting it from the subcutaneous fat to be stored in this truncal fat. I've been saying visceral, but it really is all from this truncal space, where you are having the activation of lipoprotein lipase, pulling in the fat and inhibiting the breakdown of that fat. Now, let's address what I think is a critical question, because having heard all of this, people might start to think, well, then cortisol is a key controller of fat. Well, it would maybe be a key controller, but it's not the key controller. That is still very firmly in the hands of insulin. So let's just look at how does cortisol's role in fat storage compare to insulin's, and can cortisol drive fat gain alone? I have long emphasized that insulin is the primary driver of fat storage. Insulin activates lipoprotein lipase to promote triglyceride uptake. It inhibits HSL, that hormone-sensitive lipase, in order to block lipolysis or the breakdown. And it also upregulates a critical transcription factor called SREBP1C. That stands for sterile regulatory element binding protein 1C. So SREBP1C. That is the transcription factor that induces lipogenic enzymes. So helping the fat cells store fat, like fatty acid synthase, FAS. That's one of the key enzymes that gets activated in response to SREBP1C, which itself gets activated in response to insulin. Now, these actions are potent across all adipose tissue, but especially subcutaneous fat. Now, of course, cortisol, by contrast, is primarily enhancing the fat uptake and storage in visceral fat. Studies in rodent models of Cushing syndrome show that cortisol increases visceral fat mass, but the effect is amplified by insulin. But to test whether cortisol alone can drive fat gain, let's consider untreated type 1 diabetes. This is a condition commonly called diabulimia, but where insulin is absent, of course, in the case of type 1, because of the autoimmune destruction of the pancreatic beta cells. So in a person with type 1 diabetes, they have the horrible power, the tremendous temptation to abuse their insulin therapy and deliberately underdose their insulin in order to stay thin. And of course, it works very well, but at a tremendous cost. Now, in this state, the metabolic stress from uncontrolled hyperglycemia and ketoacidosis actually elevates cortisol levels. Now, a study done by Dunger et al., this was in '88, found that newly diagnosed untreated type 1 diabetic children would have both this extraordinary wasting away of their fat cells. So they're losing fat mass almost by the minute. They cannot hold any fat on their bodies. They're wasting away. They're getting scrawnier and scrawnier. And yet their cortisol has spiked considerably, going multiples higher than it normally would. So despite the high cortisol combined with an incredible appetite, so they're eating a lot, the absence of insulin is alone enough to totally prevent any fat storage. And indeed, they have uncontrolled fat depletion. They are totally unable to retain any fat just because of the loss of insulin, even though they're eating a lot, even though cortisol is up. So the example is telling. Without insulin, cortisol's lipolytic and fat storage effects with LPL activation are insufficient. They cannot overcome the lack of insulin. So while cortisol can affect the distribution of fat, particularly promoting greater storage in the visceral abdominal space, insulin is nonetheless essential for actual fat storage. So you could say that cortisol influences the location, but insulin is still the one that's in charge of how much is going there. Cortisol's metabolic effects do affect the brain, and there it influences appetite and food cravings. And wouldn't you know it, it particularly increases cravings for carbohydrates. Cortisol crosses the blood-brain barrier and once again binds to glucocorticoid receptors in the hypothalamus and the amygdala. These are both regions involved in hunger and reward, so people feeling good about what they're doing. Now, in the hypothalamus, cortisol upregulates a protein called NPY, neuropeptide Y, and another one called agouti-related protein, AGRP. And these are increased in response to the glucocorticoid response elements. And when they're activated, they stimulate appetite. At the same time, cortisol inhibits leptin signaling, reducing satiety potentially. But separate from that regulation of appetite, in the amygdala, cortisol enhances dopamine release, so increasing cravings for very palatable, energy-dense foods. Now, several studies confirm that cortisol specifically increases carbohydrate cravings. Chow et al. In 2017 found that higher baseline cortisol levels predicted increased cravings for carbohydrates and starches over a 6-month period. But similarly, Lagro et al. In 2019 showed that food cue-induced cortisol increases correlated with cravings for carbohydrate-rich, highly palatable foods. And then in last one, in Cushing's disease, Geiger et al. In 2016 reported that higher cortisol levels were associated with increased cravings for sweet and savory carbohydrate-rich foods, which decreased as cortisol was fixed. That's important. So the people with just straight Cushing's syndrome or Cushing's disease, when they had high cortisol, they were much more responsive and craving these carbohydrate-rich foods. But as the cortisol came down through treatment, so too did the cravings. Now you can sort of compound all of this. So as the cortisol goes high, they're craving more carbohydrate-rich foods, which is going to be spiking the glucose even more than the cortisol is already spiking due to its effects at the liver. Even further, as they continue to eat these foods and insulin is spiking all the time, the high insulin alone is capable of driving insulin resistance, but then the cortisol itself is further exacerbating insulin resistance, pushing the insulin up, promoting even more weight gain. So it's a perfect storm metabolically. Now, in summary, as we wrap up, cortisol is, in fact, a multifaceted hormone that, when chronically elevated, will profoundly disrupt metabolism. It is promoting gluconeogenesis by activating enzymes like PepsiK and glucose-6-phosphatase. That's causing this hyperglycemia. At the same time, it's causing insulin resistance through ceramide biosynthesis and accumulation. The collective effect, or the combination of those, is what explains the dramatic increase in type 2 diabetes when cortisol is chronically elevated. Underlying all of this are these pathogenic changes in how the body stores fat, with a much greater, or a promoting environment of storing fat in the visceral and central adipose tissue at the expense of the healthy fat storage in the subcutaneous space. But as much as cortisol does have an effect on fat storage, absolutely it does, it still is not sufficient to act without insulin. Insulin still reigns supreme, as, for example, reflected in the untreated type 1 diabetic, where cortisol is elevated, insulin is absent, and no amount of eating can make that body store any degree of fat. And then lastly, cortisol has a central effect, promoting not only appetite and hunger, but specifically increasing a craving for carbohydrate-rich foods. Not a lot of good. Now, lest it sound like I have painted cortisol as a uniform villain, it is a hormone that is essential. The absence of cortisol will, in short order, lead to an absence of life. It is lethal. We need its ability to help the body mobilize energy. In its absence, there's insufficient energy going into the blood in instances of, say, fasting, and the body isn't going to last too long. Thanks for joining me in this exploration of cortisol's myriad metabolic effects. I hope that you feel like you've learned something new and valuable. After all, more knowledge, better health.